Hello students, welcome to the fourth lecture of your course Thermodynamics. So in the previous class I have taught you about the processes. So a system undergoes a processes if it changes state from one position from one state to another. If it goes from one state to another, it undergoes some process. Here we have seen in this lecture we'll see a special case of a process which is of mass importance, that is as a quasi-static process. It's a very slow process, and it is a its process is a succession of near to equilibrium states. So if a process under to a number of infinite states, a process where the system undergoes a number of infinite states which are near to equilibrium states, then that process is a quasi-static process, and so it is a very slow in slowness is its characteristic features. So and so from so we have seen that it is very idealistic process, and it is not a true representative of an actual process, but in many actual processes are closely approximated with some negligible error. However, we are why we have taking interest in quantitative process, because of two reasons. One is they are easy to analyze, and another is the work, whatever the work producing devices that deliver whatever the work that deliver the work, that we can compare with these results with this quantitative process, because we got the maximum amount of work we can obtain from the quasi-static process. So they are can the actual process, whatever the work obtained in actual process, that can be compared with this quasi-static process. And a process, as we talk about the process can be a non-flow a flow process. A non-flow process we can see as for a closed system, because we have seen that closed system there is no mass interaction. So it has got the non-flow process, the mass is fixed. So substance which is being heated in a closed cylinder, whatever I have shown as a process, that is a closed cylinder that undergoes a non-flow process. So there is fixed mass within the defined boundary is undergoing a change of state. So however, in case of open system, we see as a an open system this undergoes a flow process. So the whatever the it in the flow process, the amount of mass is entering and leaving through the boundary. And we have seen in the practicals, we have large number engine applications are turbine, pumps, boiler, condenser, or the open system where this flow process occurs, and we have considered this as a steady flow process. There is also term as a steady flow, because this is the whatever the properties that are not varying with time. So because it occurs for a long periods of time, so it is classified as a steady flow devices. So it is also somewhat idealized process. So this is defined as a process during which a fluid flows through a controlled volume steadily without the whatever the properties, these are not changing with time at that instant. So fluid properties can change from point to point with the control volume, but at fixed point they remain the same during the entire process. So this is a steady flow process, and this is also idealized to determine the flow characteristics, determine the thermodynamic properties, change in thermodynamic properties for devices like turbine, pumps, boilers, etc. So now we see the cycle. If a system is undergone a series of processes and it comes back to the initial states, then it completes a cycle. Cycle means a system undergoes some processes from initial state and it came back to the same state again, then it is a cycle. So there is end states are identical. So if this is here, its system is undergoes 1 to 2, then 2 to 3, then 3 to 1. It goes under to 3 different processes, but it reaches the final states are identical. So it's the process under, so it is a system undergoes a cycle. Now we see the point function. So we have seen that properties are the point functions, those are the state function also we can say, because so we can locate a property at any point of the system. So if you see here, this is a state. So here this state can be defined using two different properties. So P and V has an identical values at there. So we have got a, so properties are the point function. So we can specify the pressure at this point. So here pressure, temperature, these are the points, and whatever the difference we are getting, that will be an exact differential. We simply subtracting the final value of that state, the final value of the properties at the final state from the, for the value of the properties at the initial state, whatever the difference we will get, that will be single value, and that can be that is an exact difference. We can simply subtract, we can do that. However, the pot function, so some of the quantities which are depend on the whatever the pot they are following to carry out the, to undergo the process, they have, so like here, if this system undergoes a process by following this 1 to 2 pot, or it can also reach that 2 point final step either going from 1 to 3, then 3 to 2. So it follows different pots. So at that case, if the quantities which depend on the pot of the process, those are the pot functions. Like, so certain which cannot be located, it cannot be located by the points of the system. So it is defined by the pot of the system. So those are the heat and work, and these are the energy in transition. These are the inexact difference. So we cannot, like, simply subtracting, we cannot get their values. So these are to take the integration. So whatever the area contains under this process, that will be the, here in case of that is, it is a PV diagram, so we get the work done. So for process and process B, we got a different work done. So because they have different pots, they are following from 1 to 2, and for if you take the system which is undergoes from 1 to 2 using process B, and if the system undergoes a process A, then whatever the work done is more for process B than compared to process A. So work and heat are the pot function. So normally operator delta is used to denote the inexact differential, and operator D is used to denote the exact differential. Okay, thank you. I have concluded the class here today.